I made a video for lessons 95, 96, 97. And then I turned around and made a video for lessons 99, 100, 101, inexplicably just ignoring lesson 98. So that's what this is going to be about. This will be a little short one just covering lesson 98. And it turns out that's serendipitous because I made a mistake in the video for 99, 100, and 101, specifically in the lesson for 100, which I will correct at the end of this short little video here. So there we go. Works out great. Lesson 98 is about scale factor. Now, you already just talked about similar triangles, and we saw that we can set up ratios between the lengths of the sides in similar triangles, and it doesn't have to be triangles. If we have similar rectangles, similar pentagons, similar hexagons, we can set up a ratio of their sides. Okay? Well, sometimes all we want is the scale factor. You encounter scale factors on blueprints, on road maps. Let's say you're looking at a road map and you're trying to find out how far it is from Omaha to Lincoln, and you measure on the road map and it turns out that that is 3 inches. So you look at the legend and it says that the scale for that is 1 inch equals 20 miles. So you would know then that that's about 60 miles from Omaha to Lincoln. Now, when it comes to shapes, let's say that I have a triangle here. Just made up that triangle. Nothing super fancy about that triangle at all. Here's another triangle meant to be similar to that one. I think it looks pretty close. Yeah. So they're similar, which means all their angle measures are identical. That one's identical to that one. That one's identical to that one. And that one's identical to that one. And since they're similar, that means there's some common ratio between the length of their sides. Hang on a minute. I think I just heard a cat in distress. Hang on a second. Sorry about that. It wasn't either of my cats. I think it was a feral cat outside, but I can't find him. All right. So, scale factor. Because these two triangles are similar, we know that there's a ratio, a common ratio between the length of their sides. Whatever that common ratio is, that is called the scale factor. And we can measure the scale factor from a larger object to a smaller object if you really had to, but almost always we're interested in the scale factor between the smaller to the larger. So let's say, case in point, that the length of this longest side here, the base of this, that this one is 2, and this one here is going to be 8. All right? Now, because they're similar, I don't need to know what some other dimension is to figure out what the scale factor is. We could set up a ratio and all that, but in order to set up the ratio, we need to know what the other dimensions are. But to find the scale factor, all we need to know is that they are similar and that we know at least dimension on the smaller one and dimension on the larger one. Okay? Because the scale factor is simply this. There must be some number, I'm going to call it f for factor, that if I multiply it by the smaller side will equal the larger side. So for what scale factor f does 2 times f equal 8? Well, you can see pretty easily that f is 4. So the scale factor between this triangle and that triangle is 4. So knowing that, okay, if this side, this length here is 2, and this side here, then we measure and we find out to be 3, well, we know that then this is 12. Yep. And let's say that, let's go the other way this time. let's say that we measure this over here. They're similar, right? And we find this to be 24. All right. Then we know that the length of this, since the scale factor is 4, must be 24 divided by 4 because we're going from the larger to the smaller. So this must be 6. So 2, 3, 6, 8, 12, 24. That is scale factor. There you go. Now, where this becomes really interesting is when we consider the scale factor between two shapes, and then we consider the scale factor of the areas or the volumes if we made a three-dimensional object out of those two shapes. So let's look at this example here. Let's say that we have a square that is 2 by 2. And over here, we have a square that is 3 by 3. And let's say inches is fine. Now, number one, what's the scale factor between the smaller square and the larger square? Well, the scale factor will be some value f that if I multiply the length of the smaller side, it will equal its corresponding length on the larger shape. So 2 times the scale factor equals 3. That means our scale factor here is going to be 3/2, or if you like, in decimals, 1.5. Now, all we've done in either case here is just compare the length of the sides to the length of the side. Okay? That's called a linear scale factor. Just comparing their lengths. So let's consider their areas, though. So let's say, okay, 2 times 2. So this has an area of 4 square inches. 3 times 3, this has an area of 9 square inches. Interesting. So let's do the same thing. Let's find the scale factor for their area. So to go from the smaller to the larger, I'm going to take the smaller area. I'm going to call this F sub A for area, the scale factor of the areas. Well, whatever the scale factor is, 4 times it should be 9. All right. So let's find the scale factor for the area, divide by 4. So the scale factor for the area is 9/4. Notice anything interesting? The scale factor for the area is just the square of the linear factor. 3/2 squared is 3 squared, or 9, over 2 squared, 4. So if I square the linear factor, that automatically gives me the scale factor for their areas. And in a decimal, this would be 2.25. So, if we looked at this example right here, all right, I don't know what the area of the smaller one is, or the larger one. We could figure it out, but we'd have to drop an altitude there, and we'd have to do some trigonometry and fancy stuff to try and figure that out there. But I can tell you straight away that whatever the area is, that this larger one is 16 times larger than the smaller one. Because their scale factor is 4, that means the scale factor of their area is 4 squared, or 16. There you go. Now, let's consider volume. Let's say I took these two squares here and I made boxes out of them. So I'm taking a 2 by 2 square, and we're making a 2 by 2 by 2 box, and I'm taking a 3 by 3 square, and we're making a 3 by 3 by 3 box. All right, so what's the volume of this 2 by 2 by 2 box? Well, it's 2 times 2 times 2, which is 8 cubic inches. And the volume of this larger box is 3 times 2 times 3, which is 27 cubic inches. Interesting. Well, let's look at the scale factor of their volume, F sub V. I'm looking for the factor that if I take the smaller one, 8, and multiply it by whatever our scale factor is, that will equal the larger one, 27. Well, that means the scale factor is going to be 27/8. Notice anything there? Yeah, you do. 27/8 is just the cube of the linear scale factor. 3 to the third is 27. 2 to the third is 8. So if I know what the scale factor is, the linear scale factor, right away, you can square it to figure out what the scale factor of their areas is, and cube it to figure out the scale factor of their volumes. Yes. And you recall that area is measured in square units and volume is measured in cubic units, so it all makes sense, doesn't it? Yes, it does. All right, splendid. Let's look at the problem set. Here's problems A and B. Okay, we have blueprints. All right, so there's a blueprint that shows the little house, little whatever. If the length of a wall on the blueprint was 6 inches, what was the length in feet of the wall of the house? Okay, all right. Well, be careful here because we're asking for inches on one thing and feet on the other. In order to compare those, we have to either make them all feet or all inches. But we can do that at the end of this problem. So let's just deal with inches. Okay? So we've got a blueprint. We're drawing a scale of 1 to 24. The length of a wall on the blueprint. So we have a room here. Maybe there's a door right there and a window. Yeah, at any rate, on the blueprint, the length of this wall is 6 inches. Well, the scale's 1 to 24. That means on the actual wall, the actual building, in the actual house, whatever it is, that I'm not going to draw this to scale. The number of inches will be 6 times 24. So what is 6 times 24? Well, it's 144. So the scale factor tells us that 6 inches on the small diagram is equal to 144 inches on the large diagram. Well, 144 inches is 12 feet, right? Sure, because 12 inches per foot. So 6 inches on the small diagram is equal to 12 feet on the large diagram. You know, we can take that a step further if we like. Okay. They gave us a scale of 1 to 24. But let's give it a scale between inches and feet. Well, 6 inches is equivalent to 12 feet. That means 1 inch on the blueprint must be equal to 2 feet on the actual house. I'm missing my eye there. Yeah. So 1 inch is to 2 feet. There we go. So which way you did it here? We've got our conversion from inches into feet. That means 6 inches on the blueprint should be 6 times 2 or 12 feet on the house. There you go. All right, Brett is carving a model ship from balsa wood on a scale of 1 to 36. If the ship is 54 feet long, the model ship should be how many inches long? All right. Well, I'm sure I don't know, but we can figure it out. Just as before, we're comparing something that is feet with something that is inches. So again, we either are to be all feet or all inches so that we can set up a scale like we did here that takes us between inches and feet. So to do that, let's start. We could do that at the end or we could start at the beginning. I'm going to do it at the beginning. I'm going to convert 54 feet to inches so that I can use this scale factor, because this scale factor is just the number of inches from one to the other. It's not the number of feet. Okay? Could be the number of feet, but 36 is going to 54, nice and even. So I'm going to convert this to inches. So 54 feet. To convert feet to inches, we multiply that by 12 inches over 1 foot. So our feet cancel out. You guys have done this kind of thing many, many times. So 54 inches would be 54 times 12. 54 feet times 12. 54 times 12 is going to be 50 times 12, which is 600, and 4 times 12, so 648. So 54 feet is 648 inches. Now I can use my scale factor. So we have the larger ship here. 54 feet long. And maybe it's the size of a smokestack. I don't know. Then we have the smaller ship here. Okay, so we know that, let's say the size of the smokestack here is 54 feet, or now we know 648 inches, and the scale is 1 to 36. That means to find the size of the smokestack on our model, since we're going from the larger to the smaller, we divide by 36. So we need to take 648 divided by 36. And wouldn't that be nice if that went in evenly? And I suspect it does. We know that whatever it is, that 36 only goes into 64 one time. And I'm just gonna make a guess here, because if I whatever this number is, when multiplied by 6, it equals 8. It's can only be 8 rather. But let's double check that, because I guessed at that. Is 36 times 18 648? Well, I don't know. 36 times 18, 6 and 8 is 8. Carry the 4, 24. Oh, look at that. That's 288. Yes, and then put a 0. 6 and 1 is 6, and 3 times 1 is 3. So that is 8. That is 4. Carry the 1. 648. There it is. 8. So that means on our small little guy here, that's going to be 18 inches long. Yeah, 18 inches long. So what we've shown is that a scale factor of 1 to 36 is equivalent of 18 inches on the smaller ship to 54 feet on the larger one. Well, that's an equivalency, if you will. You can break that down, of 1 inch equals 18 goes into 54 3 times. 3 feet. So there's a good scale factor right there that compares between inches and feet, not just inches and inches. So on the model, if I know what the inches are on the smaller one, I convert that to feet by multiplying by 3. If I know what the feet are on the top one, on the larger one, I convert that to inches by dividing by 3. So there's your good little scale factors right there. Lovely. Lovely. All right. Solve by using scale factor. Now, before when presented with problems like this, we would cross multiply. We'd say, oh, well, 5W must equal 7 times 15. And then we could solve for W. But now, let's see if we can't do this perhaps an easier way by using scale factor. It's not always the easier way, but when the numbers are simple like this, it's much easier. So remember that we're comparing a fraction to a fraction. That means we're comparing a ratio between this fraction and that fraction. And the ratio exists if we compare the fraction to the fraction, if we compare the numerator to the numerator, or the denominator to the denominator. So in other words, this to go from 5 to 15 required a scale factor of 3. That means the scale factor for the denominator must be the same. That means W here must be 21, or 7 times 3. 5 times 3 is 15, so 7 times 3 is 21. There you go. You just solve W using the scale factor. No cross multiplying, none of that beeswax. All right, do the same thing here. Okay. Let's look at the scale. We see 3 and 21. Clearly, the scale factor there is 7. 3 times 7 is 21. So we're going this direction. We're going from the larger one to the smaller one. The scale factor is still 7, but this time, since we're going from larger to smaller, right to left, we are dividing. 42 divided by 7 is 6. That means x here is equal to 6. So 6 over 3 is the same as 42 over 21. And that's certainly 2, because that's 2 and that's 2. All right, so using the old scale factor. E. These two rectangles are similar. Calculate the scale factor from the smaller rectangle to the larger rectangle. All right, well, we can calculate the scale factor easily enough. We could choose any sides here as long as they're corresponding. I could go from 4 to 10, or I could go from 10 to 25. You know what? I'm going to go from 4 to 10. So that means there's some scale factor, f, that if I multiply the length of the small side, it will give me the length of the corresponding side on the larger triangle. So 4 times the scale factor equals 10. So f should equal 10 fourths or 5 halves, which is 2.25. All right, so there's my linear scale factor right there, from the smaller to the larger, smaller to the larger. So then f says the area of the larger rectangle above is how many times the area of the smaller rectangle. Golly, okay, all right. Well, we can do this, right? We know that the scale factor for the linear measures is 5 halves. That means the scale factor for the areas of these two must be 5 halves squared, which is 25 fourths, which is 4 goes into 25 4 times with a remainder of 1. No, someone doesn't. I'm just going to convert that to decimal. So 4 goes into 25 6 times with a remainder of 1. Yeah. So 4 goes into 10 2 times with the remainder of 2. So 4 goes, 6.25. I should have seen that much sooner than that. So the answer to the question, how many times larger is the area of the larger rectangle than the smaller rectangle? Well, 6.25 times. It's the square of the linear factor. There you go, scale factors. Pretty straightforward, pretty simple. Let me know, as always, if you have any questions. And lastly, in lesson 100, at some point, you are asked to estimate the square root of 700. And specifically, you're asked to find 2 consecutive integers that this is between. It'll make more sense when you do that. And when I showed you how to do this in the actual video lesson, I showed you how to determine that it was somewhere between 20 and 30. So the square root of 700 is greater than 20, but less than 30. So somewhere in between those two. But that's not what they're asking. They're asking for the actual integers, and you use your calculator for this, but it turns out that 26 is 26 squared is 676, which is less than 700, and 27 squared is 729. So even better than saying between 30, we know that whatever the answer for the square root of 700 is, it must be between the square root of 676 and the square root of 729. So it must be between 27 and 26, somewhere between those two. This is the number they were looking for, not 20 to 30. Again, that sounds like gibberish right now, maybe, but hopefully by the time you get to that video lesson, that'll make complete sense. So the answer I should have given you was 26 and 27. Not 20 and 30. 26 and 27. Okay, excellent. Splendid.